old building in the last few days, you'll probably have noticed that the stone facing the building is rotting. You can notice it in downtown Toronto, and many of the buildings built of red sandstone. The gate posts and the facing stones around the windows are cracking and breaking away. You may not have realized it, but this is, once again, a geological process going on before your very eyes, and of course a problem if you happen to be the owner of the building. It's important not only in buildings, but also in mountains. It's a breakdown of rock and the wearing away of rock. It's important in another way that you may not have suspected. It's important as an element of what the biologists call a food chain. A food chain is exemplified by the fact that cows eat grass and we eat cows. In other words, there's a chain from grass to cows. And you may ask, what has this got to do with the breakdown of rock and geology? Well, what it has to do is that if you go back beyond the grass, you go to soil, and there you go to the breakdown of rock. In other words, you could calculate, if you wished, how much rock had to break down in order to make your steak. I remember seeing a figure once, and I think it's about 4 tons. If we were to go into detail in the breakdown of rock, we'd have to go into a great deal of chemistry. We don't do that because the programs are designed for those of you with no background in science. So we've steered clear of details of chemistry. Nevertheless, you will be faced with atomic models again. The first half hour of this hour is taken up with the Planet of Man program, The Uneventful Day.
This cut through which we're traveling is typical of the general relationship there is between geology and scenery. It's an ancient fracture in the Earth's crust, a geological fault. And it means that at some time in the distant past, the two sides of this cut moved relative to one another and caused earthquakes a very long time ago. And the resulting fracture constitutes a line of weakness where the rocks are broken. And hence, the effect of weather, rain, streams, and the Ice Age has scoured out this channel through which we're passing. It's a common observation that most scenery in this world depends very largely upon the underlying geology. The existence of this river and of many other features, like Niagara Falls, like mountains, these things are, for the most part, indications of the underlying geology.
In the limited span of the human life, natural catastrophes are major events. They have a beginning and an ending, an expression of force in perceivable time. But above all, they are immensely and spectacularly destructive. In less than 30 minutes, an erupting volcano can obliterate all traces of a nearby town, eliminate life with clouds of poisonous gases, and bury it beneath layers of ash and lava. Coming with less warning, and for that reason perhaps more terrifying, a severe earthquake may level a city in a few brief minutes, taking lives in the thousands, doing damage in the millions. These are the natural catastrophes as we most frequently perceive them. Catastrophes as events observed and chronicled throughout our history. The Day of Judgment, Armageddon, the Apocalypse. In the Bible, St. John the Divine predicts that it will come accompanied with just such events, spectacular and ultimately destructive. The Apocalypse +1. A plain, totally empty. The mountains, the hills, all have been leveled to form the last resting place of mankind. But in our day-to-day lives, we rarely live with such cataclysmic events. And there are few places on the globe that are truly level and without some form of life. The earth does indeed move and change beneath our feet. It always has. But so slowly, so steadily as to be almost invisible to the human eye. These movements are not events, but rather processes. Comparatively few catastrophic events have been responsible for shaping the world as we know it. Rather, the surface has been contorted, molded, and cut by these slow and imperceptible processes. It takes tens of millions of years for a mountain to be pressed up from the earth, and many more for the rain and the wind to wear it once more to the earth. It takes thousands of years for a river to carve a few feet off a canyon wall or cut its channel a little deeper. And as many years for rains to notch a mountain peak. Or for wind-blown sand to chew a few inches into rock. Operating in the immense expanse of geological time, made up, as it is, of millions upon millions of uneventful days, these seemingly minute forces have created the variety and the beauty of the land about us. Though they pass largely unmarked in the histories of man, they are a far more powerful agent of change than every volcanic eruption, every earthquake, since the beginning of time. The story begins here, along the point of contact between two of the great mobile plates that compose the Earth's crust. When they converge, one upon the other, intense pressures fold the land upwards to form massive ranges of mountains. The youngest of the world's ranges, the Alps, the Himalayas, the Rockies, provide us with an idea of the majesty of these uplifted giants. Their present appearance of peaked individual mountains separated by deep valleys is the result of erosional processes at work over the millions of years that followed their creation. In the perspective of our own lives, it is difficult to conceive of water as the great leveler of mountains. Water as ice, seeping into fissures and cracks, breaks up the surface rock by repeated freezing and thawing. Water as snow, moving as great avalanches, transports loose materials to the land far below. Day after day, falling from the sky as rain or running down from the snow melting on their crowns, water carries the mountains down to sea level, a teaspoon at a time. And in time, a day becomes 1,000,000 days, and a mountain of rock changes shape. Erosion begins on the newly formed mountains as a rivulet, working its way down along a path of least resistance. Then the rivulet becomes a stream, the stream a river, and the river begins to carve its own channel, chewing through rock, a flake at a time. As the river channel deepens, the banks created on either side collapse, widening the trough it flows through. After 1,000,000 years of persistent erosion, the river carves out a valley with a distinctive V shape. But in the ranges of the world, there are many valleys that would appear to have been formed by additional forces. The valley floor seems far too wide, the slopes far too severe to have been cut by the proportionately small river meandering through its basin. Once V-shaped, they were altered during the ice ages, when immense glaciers advanced through them, carving out the floor and planing the slopes. As the valleys are being carved and the peaks far above them cut to points by constant weathering and erosion, the mountains are reduced over millions of years, worn to nubs like frequently sharpened pencils. The ancient Appalachian Range, once probably as high as the Himalayas, and now smoothed to gentle rises, provides a graphic example of the effective force of erosion. Even more ancient, and inevitably more eroded, are the mountains that once towered here on the Canadian Shield. Only a few sparse roots remain today, rising stubbornly above the plain, a testimony to the impermanence of seemingly invulnerable rock. The process of erosion, as we can see it in the mountain areas of the world, is a more rapid and dramatic expression of what goes on daily on the more level surfaces of the land. The Grand Canyon, a spectacular revelation of the power of water flowing over a relatively flat topography. Some 10 million years ago, the river we now know as the Colorado flowed across a plain that was being slowly uplifted from sea level. Progressively, the river chewed its way through the rocks beneath it, channeling out the deep chasm it moves through today. In a way similar to that of mountain rivers, the Colorado has carved itself a V-shaped valley, but the spectacular shapes to be found within the canyon are a direct result of the simple fact that some rocks are more resistant to erosion than others. Composed of sediments deposited by seas that advanced and withdrew successively over a period of some 2 billion years, this area displays an obvious stratification of rock in horizontal layers. The relatively soft form slopes. The more resistant, cliffs. All combine to form a dazzling and awesome display of lines and angles, severe as geometry. The beds near the top of the canyon, the last deposited, are of varying hardness. As the river worked its way through these beds, the softer layers from time to time collapsed. As with the mountain valleys, the result was a progressive widening of the channel. As the river chewed its way ever deeper, it began to cut through the hard crystalline rocks that were formed under heat and pressure more than 2 billion years ago. Less yielding to erosion, these rocks remain intact and form the walls of the inner gorge. "60 miles beyond the rim of the Grand Canyon, the petrified forest. Slashing rain and a driven wind have gnawed away at the alternating layers of mudstones, claystones, and sandstones to produce spectacular badlands. Protected by harder rock layers, softer material often remains to form stems for stone umbrellas. Recent studies show that on steeper slopes, about 1/4 of an inch of soil is washed away every year. The presence of different minerals produces striking color variations. In the painted desert, varying amounts of iron oxides are responsible for the wide range of red tones. Imagine for a moment that the rock layers of the Grand Canyon are tilted. In the Sandia Mountains of New Mexico, the hard crystalline granites appear at the surface, and the horizontally bedded limestones and sandstones sit on top, slanted at an angle of about 30 degrees. This is often how the rock deposits are arranged on the continents, the result of folding and faulting through the ages. The granite, instead of forming vertical canyon walls, weathers into spires and peaks vaguely reminiscent of landscapes in Oriental paintings. The limestone, once lying above the granite, has weathered away to a distant white wall leaving no remnants of its passing. The Sandia Mountains and the Grand Canyon. Similar rocks arranged in a dissimilar way. When the forces of erosion work upon these surfaces, the landscapes will predictably possess variety. In New Mexico, the jagged projection of ship rock rises as a dramatic example of differential erosion. The remains of the neck of an ancient volcano, it is composed of once molten rock that solidified on its way to the surface. In time, persistent erosion has weathered away the huge cone that once stood over it and the land that surrounded it, leaving shiprock, a petrified dreadnought guarding its placid sea. Many vestiges of once active volcanoes are scattered across the world's continents. In the midst of Montreal, Mount Royal. In Edinburgh, Castle Rock stands in the center of the city, once the heart of an ancient volcano, now the foundation of a fortress. When rock layers are so arranged that harder, more resistant beds sit above the softer ones in a vertical sequence, the process of erosion tends to create an escarpment formation. Along the Niagara escarpment, the softer rock has been eroded back, undercutting the harder cap rock. This action can only progress to a certain point before the sheer bulk of the overlying rock collapses unsupported. A more rapid erosion is taking place where the Niagara River boils over the escarpment. Over a period of time, successive collapses of the unsupported ledge have moved the edge of the falls further up the river, leaving behind the deep cavity of the gorge. Although initially a seemingly incongruous comparison to Niagara Falls, these butte and mesa formations of the arid American Southwest were, in fact, created by a similar force. Numerous rivers once torrented over this area, cutting deep gorges like Niagara in many directions. Long vanished, the rivers left these escarpment forms to weather by the much more gradual force of wind-blown sand. On the top of one precipitous mesa, the Indian town of Acoma. According to some authorities, it is the oldest continuously inhabited community in the United States. In all cases of erosion, the forms that are created, the forms that add such beauty and variety to the land, are paradoxically created through destruction, the destruction of rock. This destruction takes two quite distinctive forms, physical and chemical. The two can create quite different forms upon the land. The most rapid and obvious physical weathering is effected by ice. Water, seeping into the cracks and fissures of a rock surface, expands when it freezes and gradually fragments the rock. The other forms of physical weathering are, by and large, all variations on a theme of persistent abrasion. The sea strikes repeatedly at a coastline over millions of years. A river eats away at the bedrock beneath it. And when the water is gone, in the dryness of the desert left behind, the wind dashes fine particles of sand against rock, wearing it minutely but persistently. Persistence is the key. Persistence and time. Time is important too, to another form of weathering, chemical. The corrosive solution that is formed when water combines with certain minerals does the same work as that of persistent abrasion. Rain combines with carbon dioxide as it falls through the atmosphere to form a weak acid. In sufficient quantity, this acidic solution will dissolve rock. Limestone is particularly susceptible. These natural caves have been formed through chemical attack. Some of this dissolved limestone is redeposited to build up the stalactites and stalagmites found on the roofs and floors of caves. The processes of physical and chemical weathering are working on every exposed surface of every continent, every day. They have altered the shape of the land, a little at a time. But the process will pass largely unobserved. For though it is working for every moment of every day in all the years of our lives, the days of the land will seem uneventful. Its forms unchanged in a lifetime, or two, or three lifetimes. A human identity carved in granite might endure the force of weathering for 300 or 400 years. A mountain endures for tens of millions of years. In the end, the force that works unseen through each uneventful day will, sooner or later, end the dynasty of both names and mountains.
The film you've just seen concentrates on the processes by which rock shatters, the mechanical breakdown of rock, the physical weathering processes, as they're called. The kinds of processes that lead rocks like this granite in the Arctic, on Devon Island, in fact, in the mid-Arctic, to shatter and break and to fall into streams in angular fragments. This granite in California, however, has evidently decayed in a very different fashion. The outcrop is rounded rather than jagged, and the sand at the foot of the little bluff clearly indicates that the granite has begun to break in a very different way, begun to decay in a very different way to the granite in the Arctic. This basalt is rather like the granite that you saw in the last slide. It's clearly very breakable, and it seems to be breaking down in layers, layers which peel off rather like an onion. It clearly contrasts very markedly with the fresh basalt here, this angular, jagged piece of fresh basalt that we broke with a hammer. Clearly, too, this granite is not at all the rock that it used to be, and not at all like this fresh granite. Clearly, this granite and the basalt have begun to break grain from grain. The coarse interlocking texture of igneous rocks that we looked at when we looked at the formation of igneous rocks, the cooling and crystallization of igneous rocks, has been lost. The rocks are beginning to disintegrate grain from grain. Evidently something is attacking the minerals. If we look further at what's going on and examine specimens like this, we find that on this fresh surface, which has no relief, just rather jagged as it broke with a hammer, the dark crystals, which are garnets, and the pink material, which is mostly feldspar, don't have any kind of relief at all. It's just a fresh break. But on this specimen, we can see that the garnets are beginning to stand out like beans almost on the surface of the specimen. This is a specimen which has been exposed at the surface, and evidently the material between the garnets has been worn away in some fashion, while the garnets have remained standing out from the specimen. We call this differential weathering, and we find the same kind of thing in this specimen here, in which there's a vein of rather pinkish material, which in fact is dominantly quartz with a little bit of feldspar mixed in. And that vein stands out quite clearly with a relief of about an inch from the rather dark material which surrounds it. That dark material, in contrast to the small vein, is formed mostly of minerals which are rich in iron and magnesium, the ferromagnesian minerals, things like pyroxenes and hornblendes. The specimen behind it also shows this phenomenon of differential weathering, but it's a sedimentary rock, and the reason is rather different. We'll come back to it later. Now, why should that kind of differential weathering occur? Why do some parts of igneous and metamorphic rocks, some minerals of igneous and metamorphic rocks, stand out and remain on the surface as obvious features like the garnet, while the material around, the mineral around, decays and breaks? Why do some granites just break like some very breakable piece of plaster, for example? Well, the answer to that lies in the minerals themselves. Remember that the minerals of igneous rocks, like olivine and pyroxene and amphibole, biotite, and so forth, are formed at a high temperature, the highest being those rich in iron and magnesium, and the lowest being quartz, and the temperature range being from perhaps 1500 degrees down to 600 or 700 degrees. Clearly conditions deep within the earth, and yet on the surface of the earth those minerals are subjected to an atmosphere rich in carbon dioxide, oxygen, and water, a totally foreign environment to the high pressure, high temperature environment in which the minerals formed. Now, as you might expect, the reason why some minerals persist, whereas others decay around them, so to speak, is that those which were formed at the highest temperatures are most unstable when they're exposed on the surface of the earth to carbon dioxide, water, and oxygen. And those which are formed at the lowest temperatures during the crystallization of an igneous or a metamorphic rock are less unstable when they're exposed on the surface of the earth. So the garnet, for example, one might conclude, was formed at a lower temperature than the feldspar which surrounded it, and the feldspar has decayed while the garnet has been able to persist. In this specimen of basalt, the first mineral to decay is olivine, and the next would be pyroxene. And the way that the olivine decays is hinted at by the color of the basalt. It's rather rusty, as you can see, a sort of a rusty brown. And that is the hint that tells us how the pyroxene and the olivine have probably broken down. In fact, that brownish color is iron oxide. It's the mineral limonite. And the process by which the limonite was formed is by oxidation. And sometimes, instead of limonite, we get another iron oxide that you already know, hematite. These then are minerals produced by the oxidation of the iron which is present in the olivine, pyroxene, and also in amphibole and biotite. The iron in the original minerals is bound up in the crystals of the silicates, but when exposed at the surface, that iron combines with oxygen to produce limonite and hematite, iron oxides. The process by which the limonite and the hematite are produced from the iron in those silicate minerals is rather akin to the rusting of a nail. If we take an ordinary nail, an ordinary iron nail, and immerse it in water which is in contact with the air, and therefore there is oxygen dissolved in the water, we can watch what happens with time-lapse photography over a period of about 12 hours. Clearly the nail is beginning to rust. The iron in the nail is being attacked, or gobbled up if you like, by the oxygen that's dissolved in the water, and the mineral limonite is being formed. We call it rust. And eventually the nail, if it rusts sufficiently, will break. Now, clearly what happens in nature to iron-rich silicate minerals like olivine and pyroxene is a little more complex than what happens to a nail in a bowl of water. First of all, the nail is simply pure iron. In the case of the iron silicate, there's not just iron there, there's also silica, the oxygen-silica tetrahedra, you remember. And while the iron oxidizes and goes to form an iron rust, limonite, the oxygen silicon tetrahedra are dissolved in the water. Now, not only is the iron silicate different to the nail in nature, but also temperature is important. And we can see that from specimens like this. This is a piece of schist, a schist rich in iron silicates. It was collected from Georgia, and the weathering product on the surface, the iron oxide crust, is very red. It's dominantly the mineral hematite. The soil in areas like this, where one can collect specimens that have weathered hematite red, is often blood red. This is a road cut in Yosemite National Park in California. And like Georgia, the climate is warm, the rainfall is seasonal, and the result is red weathering soil from igneous rocks that are beneath the soil surface. If that rock specimen, if this one here, were in the Sudbury area, then it would weather brown. Brown like the basalt that we looked at first, a rusty, anonymous-looking brown. It's the difference in climate which causes the iron mineral to be different. Hematite in warm climates with seasonal rainfall, and limonite in the temperate Sudbury area. Now, the other thing which can cause a difference in the color of the mineral that's developed on the weathered surface is the kind of metal which is within the rock. In this specimen, which instead of being an igneous rock with the metals in silicates is an ore specimen, the color is due to the presence of nickel and copper. Clearly then, the kind of weathering color that we get on the surface of rocks and of ore specimens is a good indication to prospectors of just what sort of rock or ore is beneath the surface. Here is another specimen of ore, also from the Sudbury area, and we can see once again the kind of limonite crust that we would expect to find on an iron-rich ore or rock. And sure enough, that's what we've got. On this freshly broken specimen, we can see that the main mineral is pyrite. Now, pyrite is iron sulfide. So once again, we've got an iron-rich mineral, like an iron silicate, but instead of silica accompanying the iron, in the case of pyrite, we have sulfur accompanying the iron. Let's have a look at the atomic structure of iron sulfide and discuss just what happens to the two components of that mineral. This is an atomic model of iron sulfide, of pyrite. Here are the iron atoms, and it's these atoms which are gobbled up by the oxygen to form the limonite in the Sudbury area. The bonds between the iron atoms and the sulfur atoms, which are these here, and which surround the iron atoms, are broken by the oxygen, which gobbles up the iron. The sulfur atoms are found in then go into combination with water, oxygen, to form sulfuric acid. So just as in the silicates, the process is not just one kind of process. There are two processes: the oxidization of the iron and the combination of the sulfur with oxygen and water to form sulfuric acid, a second product that goes away in solution like the silica. We've looked then at the chemical changes that are undergone by the iron-rich silicate minerals. The iron in them is oxidized to limonite or hematite, depending on the climate, and the silica goes into solution. In the iron-rich ores, the sulfides, the iron is also oxidized, the sulfur also goes into solution, as the silica did, but this time forms sulfuric acid. Now, what about one of the other rocks that we looked at the beginning of the unit? If we look at the granite, we find that the dominant mineral component is feldspar. About 75% of the granite is feldspar. And that feldspar is the starting point for this, for clay. If we were able to look at the feldspar grains in those broken up fragments very close up, with a microscope perhaps, we'd be able to see that the feldspar grains looked rather chalky, a little white. And that is the beginning of the breakdown of the feldspar, the chemical breakdown of the feldspar. Once again, it's dependent on climate somewhat, and we only have to look at Cleopatra's Needle in New York to see that. After a few decades, the feldspar is turning to clay, whereas for 35 centuries in Egypt, the feldspar stayed perfectly fresh. So it's also a change that depends on climate. But what is the nature of that change? Well, what is the composition of feldspar? Here we've put up again the composition of potassium feldspar as our example. Potassium, aluminum, and oxygen silicon tetrahedra. If we take a piece of feldspar of that composition and we put it in a jar of water, like the nail was put in a jar of water, with access to the air, what we find is that the potassium totally dissolves. It disappears into the water. Some of the oxygen silicon tetrahedra also dissolve, and water is added. So we end up with a mineral of the composition water, aluminum, and oxygen silicon tetrahedra, and its structure is also radically different from the feldspar that we began with. Its structure consists of layers. We can represent the first of those layers of aluminum and oxygen silicon tetrahedra with this red stripe. I'm sorry, aluminum and water. And oxygen silicon tetrahedra in this layer. And a second sandwich of aluminum and water, and then oxygen silicon tetrahedra. That's the structure of the new mineral. And it's not surprising that it's the structure of the new mineral. If you remember from looking at micas, the properties of minerals with a layered structure. The minerals with a layered structure had plates which slid over one another or cleaved away from one another. In clay, the same thing happens on a microscopic scale. When I press the clay or you pot with clay, what you do is you move layers one over the other. These sandwiches are sliding. And the structure of mica is remarkably similar to the structure of the clay that we've just made. In fact, all we would have to do in order to get to mica is we'd have to add some aluminum, this quartz up here, add a little bit more oxygen silicon, another layer there, and do the same thing down here. Some potassium, oxygen silicon tetrahedra, and so on. And there we'd have a mica. We'd have muscovite mica. So there seems to be a close relationship in atomic structure and also a quite close relationship in composition between the clay we've just made and the micas. And we can see that in the atomic structures as well. This is a ball and spoke model of the same atomic structure of clay that we've just constructed. These are oxygen silica tetrahedra. These are water and aluminum atoms, and here are oxygen silicon tetrahedra again. These rather distracting connecting rods are simply to hold the model together. They're not atomic bonds such as these links are. So what we have then, we have one of those sandwiches, oxygen silicon tetrahedra sandwich and an aluminum water sandwich. And here then the bottom of another sandwich. And nothing holding the layers together. Now, that structure is similar to mica. Let's compare the ball and spoke models. The mica structure, or the Muscovite mica structure, you may remember. The essential point are the connecting atoms between the sheets. These atoms here, potassium atoms. And here are the sheets. One there, and then another one with its top down up here. And they're the connecting atoms. The structure of the clay can be compared with that structure of the Muscovite mica quite closely. This layer and this layer compare with one another. This layer and this layer compare with one another. The essential difference is that the potassium atoms that are present in the mica are missing in the clay. And that is a good hint that we can very easily make clay from mica, because we've already seen that potassium atoms are very soluble in potash or potassium feldspar. So if we can lose them in the feldspar, we can lose them in the mica too. So in fact, we've got two sources in the granite for clay. Dominantly feldspar, because it's the most important mineral, but also mica. An important process in the production of the clay was the solution of the potassium atoms and some oxygen silicon tetrahedra. Now, in the case of the mica and the feldspar, the solution was not complete. But in some kinds of chemical weathering, the solution of the mineral is quite complete. Let's have a look at an example of that. This piece of limestone is formed dominantly of the mineral calcite. And what happens to it when it's subjected to rain can be simulated in the laboratory using an artificial rainstorm. In other words, a shower head. Time-lapse photography shows what happens to this piece of limestone when it rains. The calcite, which makes up the limestone, dissolves totally. That's the first mineral that we've come across which is totally lost in solution. And it's lost in solution because the water that falls on the surface of the earth, the rainwater, is slightly acid. It's in fact carbonic acid formed by the combination of water in the form of rain and carbon dioxide, which is in the atmosphere. And that's what makes solution such a very, very important process in weathering, the slightly acidic quality of rainwater and groundwater. If this were a glass of the water which had passed over that limestone, it would be rich in calcium and rich in carbonate ions. If it had also passed over a granitic terrain, as we've seen, it would be rich in potassium. And if it had passed over other rotting rocks, it would be rich in other elements. And where do those elements go? Do they go to the sea and just stay in the sea, because that, of course, is the end point for all water? Well, they get there, but they don't just stay in solution. They are the source of sedimentary rocks like this. This limestone, formed of coral fragments, could not have been produced if calcium had not been dissolved on land, carried to the sea, and there been available for organisms to precipitate as part of their skeleton. Similarly, this salt was produced from sodium and chlorine that was dissolved in land waters and then carried to the sea. This gypsum, calcium sulfate, has the same origin. So that's the fate, or the destiny, if you like, of material which is dissolved during weathering. They form sedimentary rocks from ocean water. Now, solution is a very important process, as you've seen. We've met it in all the weathering changes that we've come across. But there's one mineral that it hardly affects at all, and that's this one. These are tiny grains of quartz, forming a quartz sand. And eventually, if that sand becomes cemented together, it'll form a quartz sandstone. Quartz is hardly affected at all by solution, but this sandstone doesn't escape solution. As you can see, the grains of this sandstone, once cemented together by calcium carbonate, are becoming disaggregated because solution has affected the cement between the grains, and it's the differential effect of solution on the cement between the grains which produces this rather spectacular rock. It's important when considering weathering to realize that what we're looking at is, if you like, a low temperature, low pressure reaction chamber on the surface of the Earth which recombines into new minerals, those minerals which were formed under great temperature and pressure beneath the surface of the Earth. Those minerals reach the surface because of the movement of lithospheric plates, allowing volcanic action and allowing molten rock to well to the surface. Even most of the gases in the atmosphere which those minerals react with were derived from volcanic activity, all except the oxygen, which was produced by plants. But even that oxygen was produced from carbon dioxide, probably largely from volcanoes. So what we're looking at, in fact, when we look at weathering, is a low temperature, low pressure reaction chamber that succeeds a high pressure, high temperature reaction chamber.